Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to your online lecture series of EE-222 microprocessor systems. This is the third lecture of week 12, your lecture number 36, and in this lecture we are going to discuss different modes of timers: prescaler, postscaler, timer interrupts, counters, and RTC. So far we have covered CLO 1, 2, 3 and 4 of your course, and currently we are at CLO 5, the last CLO of your course, and this CLO is at C4 level of Bloom's taxonomy, that is design and analysis. So in this CLO we will focus on design and development of code for real life applications. So let's start with an overview of the timers. Okay, so here is the simple block diagram of a timer in PIC microcontroller. This blue box right here is the actual timer or counter register, and then we have this purple box as the prescaler, this green box, this AND gate as the timer enable, the start stop bit of the timer, this pink box as the clock select, the clock source select register or the clock source select option. So if we are using the timer in a timer mode, the clock source will be derived from the main oscillator of the microcontroller. So the microcontroller oscillator divided by 4 will be fed as the clock source of this timer, and at each clock transition the timer will increment, this blue register will increment. If we are using this register in a counter mode, then the clock source will change, everything else will remain the same, and the clock source will be derived from some external source. So some input output pin will act as the clock source, and any transition on that pin will result in an up count in this blue register. Then this prescaler further divides whatever clock is coming at this stage. So if we are using the internal oscillator or the external oscillator, the clock will be divided by this prescaler if we have enabled it. If we do not enable this prescaler, then the clock will travel as it is after this prescaler. Then the clock will not reach this counter, this timer or counter register, this blue register, until or unless this timer is disabled. So now if you see, the timer has been enabled and the clock has traveled through or passed through this gate to reach this register, and when the clock reaches this register, it counts up at every transition. It keeps counting up until the count reaches FF, and then it overflows from FF to 00, and as soon as the overflow, the counter transition or the counter reset occurs, the overflow signal is given to the overflow circuitry and the overflow flag is set. The TMR 0123, the timer IF interrupt flag is enabled, and if the interrupt is enabled, the interrupt will be generated, otherwise the flag can be read manually at this point, this orange point before this gate. So this is the basic block diagram of all the timers in PIC18. We discussed timer 0 in our previous lecture, and we discussed all the modes associated with timer 0 module, and we could select between different timer or counter mode or the clock source using this T0 con register, timer 0 control register. So the timer 0 can be used in either 16-bit mode or an 8-bit mode. Why do we use 8-bit mode when we have an option of 16-bit mode? In case of timer 0, we know that there are two registers, the TMR0H and TMR0L. So these two count registers combine together to form a single 16-bit register. pseudo single 16-bit register. That is not an actual 16-bit register because our microcontroller is of 8-bit size. So what happens is, at physical level, there are two different registers. One is an 8-bit lower register and one is an 8-bit higher register. And to read or write any of those registers, we need separate clock cycles for both. So for example, we needed a count of greater than 256. A single register cannot count that. So we use the timer in a 16-bit mode. We combine those registers and deal them as a pseudo 16-bit register. But we give a command, we give a read-write command of one read or write of 16-bit. But what is happening at the back end? At the back end, if we go down here, there are two registers, TMR0L and TMR0H. So both of these registers will be read or written individually. So one instruction cycle will be taken to deal with this register and one instruction cycle will be taken to deal with this register. So two clock cycles, two instruction cycles will be consumed for reading or writing this complete 16-bit count or the timer register. But what if our count is less than 256? Our required count is less than 256. We can do that by using just one register of the counter. So we are excluding that overhead, that one instruction cycle overhead that was being observed while using a 16-bit mode in case of timer 0. Today we will also study the timer 1 and we will see that in timer 1 both the timer lower and timer upper registers can be read or written in a single instruction cycle. That is the property of timer 1 only, not the timer 0. So there is no 8-bit mode in timer 1, we will see that. But in timer 0, they have given an 8-bit mode to enable the read or write, separate read or write of lower and higher register. To further explain, if we have the option in an 8-bit microcontroller to read or write all the 16 bits at a same time in a single instruction cycle as it is implemented in the timer 1, then why we are not using it in timer 0 also? Why do we need the 8-bit mode in the first place if that one instruction cycle overhead can also be removed, as it is already done in timer 1's case? So the answer to that is, it is a legacy stuff. It is done to enable backward compatibility of the microcontrollers. This microcontroller, the 18F4550 we are using right now, has a 16-bit timer 0. But if you go to the older models, much older models of this PK-18 microcontroller, you will notice that the timer 0 was originally an 8-bit timer. So some programs were using timer 0 as an 8-bit timer, and then the microchips were upgraded and the older models were discontinued. So many of the devices had to replace the older microcontroller with the newer model. And if we don't have the backward compatibility, then that is an issue. We don't have replacement parts anymore. So to enable the backward compatibility, they have provided an 8-bit timer mode in timer 0, specifically in this model of PK-18 and some other models also. So 8-bit is not needed in today's designs. They have come up with solutions to remove the overhead of the single instruction cycle that is required in reading and writing the two registers separately. They have managed to do it in one instruction cycle. And our other timers, the timer 1, 2, 3, in this IC also, they have that capacity and they have that capability to read or write the complete 16 bits in a single instruction cycle. So for this microcontroller in your applications, as you are not using the legacy mode, or you are not using some older devices, you don't have to use the 8-bit mode. You don't have to use it at all. You can use a 16-bit mode and it will work fine. So that is the block diagram of timer 0, just like the one I showed here. This is the clock source select, then this is the prescaler, and then this is the synchronization with internal clock or not, and this is the actual timer register. And here we can see that this is the timer 0 IF, the overflow flag. So timer is essentially just a register, an 8-bit or 16-bit register that counts up whenever a clock pulse is given at the input. That clock pulse can be from a synchronous internal clock of the microcontroller, and in that case we call it as a timer, and that clock source can be from an asynchronous external source, from a sensor maybe, and we count the pulses on that sensor, so we call it a counter in that case. So counter and timer are essentially the same thing. Timer 0 was the simplest timer in PIC18. It doesn't have much more of a functionality associated with this timer. So there is in its control register, in the T0 con register, we have the timer on off bit, we have the mode selection bit, whether we are going to use it in an 8-bit or 16-bit mode. Then we have the clock source select bit, whether we are going to use it as a timer or a counter. Then we have the source edge select bit, that if we are using it in counter mode, the clock is coming at an external pin. So whether we want to count up on a high to low transition on that external pin or a low to high transition, and that depends upon the sensor properties usually. Then we have the prescaler enable bit. So if we do, set this PSA to 1, no prescaler will be assigned, and if it set this to 0, a prescaler will be assigned. And what prescaler will be assigned, that will further divide the clock by what value, that is decided by the next 3 bits, T0 PS0 to T0 PS2, and we can choose from these 8 options, these 8 prescaler values of 2, 4, 8, 16, 32 up to 256. So we can further divide our clock by any of these values. One thing to note here in case of timer 0 is that when we enable the prescaler, when we set this PSA bit to 0, automatically a prescaler value of 2 is assigned. So the clock is divided by 2. Students may get confused that they set this bit to 0, but they also set all these prescaler bits to 0, assuming that no prescaler will be assigned in that case. But as soon as you enable the prescaler, even if all the next 3 bits are 0, a prescaler of 2 is assigned. So your clock is automatically divided by 2. If you do not need a prescaler at all, you have to set this pin to 1. So this is all about timer 0. We have discussed it in detail. We have written a program also. Before moving on to the timer 1, I would like to open the program that we wrote for timer 0 for delay generation in our previous lecture. And in previous lecture, we will see that we were using the polling of the TMR0IF flag using a while loop, while not TMR0IF. Let me open the code, and we will see that we were manually checking that flag, the timer overflow flag. We were not using interrupt for the timer. We have studied interrupt, but we have only used interrupt for the external interrupt source up till now. So before moving on to the timer 1, I would like to use interrupt for the timer 0 as well. So this is the code that we wrote in our previous lecture. We were going to generate a waveform on port D0. We set the prescaler to what value we can see here. that 011 sets the prescaler to 16, I guess. Yes, the prescaler is 16. So whatever clock is coming from the microcontroller source, that is further divided by 16. So right now we are using the 4 megahertz clock frequency in our microcontroller, and 4 megahertz is automatically divided by 4 before reaching the timer. So 1 megahertz is reaching the timer as a clock source. Then 1 megahertz is further divided by 16. So 1 megahertz is 1 microsecond divided by 16. The frequency is multiplying by 16 in time domain. So every count will be after 16 microseconds. And how many counts we are doing here? 63661. Not 63661. 65536 minus 63661. We are doing 1875 counts. So 1875 into 16 means 30,000 microsecond delay or 30 milliseconds delay. So this program generates a 30 millisecond delay, and after every 30 milliseconds it toggles the state of pin port RD0. So for 30 milliseconds it remains high, and for 30 milliseconds it remains low. But here if we see that in the delay subroutine, we are manually polling or checking the status of this flag, the overflow flag of the timer. We are stuck here at this point. What we are going to do now is we are going to enable interrupt for timer 0, and we will let the interrupt module check this flag for us in the background. We don't have to check it. So we will just wait, and whenever the interrupt comes, we will do whatever we want to do. Okay, so we will start by including the interrupt service routine in this program. I will copy the standard format that is used to declare the ISR from our previous code that we learned in the interrupts based lecture. So here it is, void interrupt ISR, and here we will do whatever we want when the interrupt comes, and the interrupt will come whenever the timer overflows. So what we have to do here in the main subroutine is we have declared the trace T0 as the output, the port T0 as the output. We have configured the timer 0 just like we did in the previous lecture based on the timer 0. Then we want to enable the interrupts. So to enable the global interrupts, we want to set the GIE global interrupt enable to 1. Also we want to set the PEIE peripheral interrupt enable to 1, and then we want to enable the interrupt for timer 0 that we are using. So TMR 0 IE, timer 0 interrupt enable should be equal to 1. Now the timer interrupt is enabled. As we are generating a 50% duty cycle waveform, so we don't have to set it and clear it. We can just complement it, and we don't need this delay subroutine anymore. So what we are going to do is we are going to clear or delete this subroutine. Also we are going to delete this function from here. All we have to do is we have to preload the timer with the desired value that is mentioned here inside the interrupt service routine. So what happens now is the timer interrupt is enabled, port is set to 0, and now what I will do is I will turn on the timer. So TMR 0 on is equal to 1. Now the timer will be running, and then I will just wait here. Now the timer is on. It will start counting from whatever value was already inside that and keep counting until it reaches the 65536 as we are using it in 16-bit mode. And after it overflows from 65536 to 0, the timer interrupt will come. So from where we want to start counting? 63361. So what we have to do is we have to preload the timer TMR0 with 63361 initially. Then turn the timer on and then just wait. So let's assume the timer started counting from this value upwards and it reached 65536 and overflowed to 0. So the interrupt came. Now what we want to do when the interrupt came? We want to toggle the pin RD0. Then we want to reload the timer with 63361 and then we want to TMR 0 IF is equal to 0. We want to clear the flag so that whenever the timer overflows for the next time, the flag is cleared and the interrupt comes again and this loop continues. So this program will do exactly what we were doing by manually checking this flag previously in our previous lecture. So let's try to build this code. The build is successful. Now we will simulate this code in Proteus and see whether a waveform of 300 millisecond on 30 millisecond on and 30 millisecond off is generated or not. So let me open our previous design file of Proteus. It is already loaded with the lecture 31 hex file as we have updated the hex file, so it should work fine. A waveform is being generated. Let me change the time scale to 10 milliseconds. This is 10, 20, 30, more than 30 milliseconds. So if we see here, if we put it to 5 milliseconds, the trigger was not working fine on 10 millisecond knob. So I have changed the knob to 5 millisecond and let's see how many blocks are there. 1, 2, 3, 4, 5, 6 and 7. There are 7 blocks. 7 blocks mean that this pin is remaining on for 35 milliseconds and it is remaining off for 1, 2, 3, 4, 5, 6, 7, 35 milliseconds. But what we wanted to do? We wanted that the pin should remain on for 30 milliseconds and should remain off for 30 milliseconds. So there is an error of 5 milliseconds here. Now let's find out where is the error in our code. Okay, here this 65536 minus 63361 is equal to 2175. I mistakenly wrote 63361 instead of 63661. So let's change it to 63661. This means that 63661 will result in 1875 counts, and with a prescaler of 16 it becomes 30,000 counts. So I think now it should work fine. There should be no error of even a single millisecond. Let's simulate it again. Yes, you can see here that there are exactly 6 boxes and the time scale is at 5 milliseconds. So now we have generated exactly the same waveform using the timer interrupt that we did in the previous lecture without interrupt, while manually polling this interrupt flag or the timer overflow flag. So now we know how to use interrupts of different peripherals and different timers. Next, what we are going to do is we are going to see the other timers available in PK-18. As I told earlier that there are 4 timers available in PK-18. And out of the 4 timers, we discussed the first timer, timer 0 up till now. That was the simplest timer. It could be used in 8-bit mode or 16-bit mode, and it didn't have any other functions associated with it. So timer 1 module is pretty similar in working with timer 0, but there are some additional functions associated with timer 1. So let's discover what are the properties and what are the functionalities of timer 1. If we open the data sheet and go to section 12, that is timer 1 module, there are listed some different features of timer 1. Timer 1 can be used as a 16-bit timer or counter. So it cannot be used as an 8-bit timer or counter. It can only be used as a 16-bit timer or counter. So now 8-bit or 16-bit mode selection is not an option for this particular timer. Then this timer 1 is readable and writable in 2 8-bit registers or a single 16-bit register. We have an option for that. Then we have multiple options to select the clock source for this timer. In timer 0, if we see the block diagram of timer 0, we can see here that the clock was coming from either the T0 CKL pin or the F oscillator by 4, that was the system clock. But if we see the block diagram of timer 1, we can see here that the clock can come from either the internal clock here, F oscillator by 4, or there is some other option. It can come from the T1 CKL, the timer 1 clock, just like in timer 0. So it can be used as a counter, but there is this additional circuitry, the timer 1 oscillator. Timer 0 did not have a dedicated personalized oscillator with it. Timer 1 has a dedicated personalized oscillator associated with it. So just like we saw that in our microcontroller, we can connect an external crystal oscillator to provide the system clock for the main microcontroller operation. We can connect a crystal oscillator with timer 1 to provide the clock. In that mode, remember that the timer will be acting as a timer, not the counter, even though the clock is coming from 2 external pins, from an external oscillator, from an external crystal oscillator, but that will be a clock, a periodic clock. That will not be an aperiodic pulse. So in case of aperiodic pulses, your module will act as a counter, and in case of a periodic clock, your module will act as a timer. So in this case, when we connect an external crystal oscillator with these 2 pins using the timer 1 oscillator, we are still using this module as a timer, just getting the clock from outside. So what is the advantage here? It is already getting an option to get a synchronous periodic clock from an internal source, that is F oscillator by 4. So why do we want to provide an external clock to this timer? Well, let me tell you that timers are usually used to generate delays. We know that. And when we want to generate delay, we want the delay to be as accurate as possible. In many applications, even 1 microsecond error in our delay can keep accumulating and can result in a huge error over the time. For example, when we are making a clock, by clock I mean a watch, a real-time clock. What if there is a 1 microsecond error in each second? So after 60 seconds, there is a 60 microsecond error accumulated. Then after 60 minutes or 1 hour, there is 3600 microsecond error accumulated. After 1 day, the error keeps on accumulating, and after few days, your clock will either be lagging or your clock will either be leading the desired time. So we cannot afford even a 1 microsecond error in case of real-time clocks. But if we use the internal oscillator, the internal crystal oscillator of the system as the clock source to the timer, we cannot precisely set the delay. And if any of you has happened to open an actual wall clock and an actual digital clock, you could see that there is a small silver color crystal oscillator inside that, and on that crystal oscillator there is written 32.768. 32768. 32768 means that the crystal frequency is 32.768 kilohertz, or the crystal frequency is 32768 hertz. Now if we carefully think about this value, this is 2 raised to the power 15, and 2 raised to the power 16 means what? 65536. If we see in this program that we have just written, we are preloading the timer with some certain value to get our desired delay. But this preloading the timer with the desired value also results in an error of 2 to 3 microseconds or 2 to 3 instruction cycles. In this case, we didn't bother about 1 to 3 microsecond error. So we said, okay, in a 30 millisecond delay, if it is 30.001 millisecond delay, it's okay, there is a room for such a small error. But in case of a real-time clock, we don't have a room for such a small error. So what we want to do, we want to completely eliminate this step of reloading. If we somehow are successful to remove this line, we are eliminating an error of 1 to 2 instruction cycles, and the timer will just start from 0, count up to the maximum value, that is 65536, and keep reloading from 0 to 65536, from 0 to 65536. So if we have a crystal oscillator of 65536 Hz, we can simply use this value as the clock source of the timer. What will happen then? If the timer has a clock source of this much Hertz and the timer takes the same number of counts to overflow, it will count from 0 to 65536. This means that the timer will overflow after every 1 second. Precisely 1 second. What we are doing now is we are eliminating the error in our code, the error in our delay, by changing the clock source and by choosing a clock source that is more suitable to generate a delay without error. So we will not preload the timer with any value. We will let it start from 0 and we will let it count up till the maximum value, that is 65536. So after a complete count, after a complete overflow from 0 to 65536, the counter will reset, and exactly precisely 1 second will be elapsed if we are using the clock source of 65536 Hz. And this way we can use the timer 1 to make a real-time clock in our PIC microcontroller. So RTC stands for the real-time clock, and usually we use the crystal of 32768 Hz or the crystal of 65536 Hz as a clock source that is connected to these two pins of the timer. Now what is the purpose of this amplifier, NOT gate and the resistor? The crystal oscillator needs this oscillator circuit to resonate and generate a clock. If I can go to the clock options, the main clock options of the device itself, you will find the same circuit here. The primary oscillator is also having this circuitry for a resonator, and here we connected the crystal oscillator 1 and 2 pins. So the crystal oscillator is a small crystal with 2 pins. One is connected with this one and one is connected with this one, and in conjunction with this circuitry it resonates and it generates a clock of the desired frequency of which the crystal is being connected. Then timer 1 also has a prescaler value. Just like in timer 0, we had 8 options for prescaler for timer 0. In timer 1's case, we have only 4 options. So we can select between prescalers of 1, 2, 4 and 8. We cannot choose any other value of prescaler other than these 4 values. Then let's start this T1 con register, the timer 1 control register, bit by bit, the function of each bit. Bit number 7 is RD16. So this setting this pin to 1 will enable the register read write in 1 16-bit operation. So it will consume just 1 instruction cycle. But if we set this bit to 0, the read write operation will be done in 2 8-bit operations. I don't think in any of the applications that we will be focusing on will require us to use to disable this mode. So what we will do is, by default, we will enable this RD16 bit and we will enable the single instruction 16-bit read write operation of timer 1. Then the second bit, the bit number 6, is a flag. It is not a it is a status bit. It is not a control bit. So if the device clock is derived from timer 1, then this flag will be 1, otherwise this flag will be 0. So what do we mean by the device clock is derived from the timer 1 oscillator? As we see here in this block diagram, that we can connect a crystal oscillator with timer 1 to provide a dedicated clock to this particular peripheral. What else we can do is that we can use this oscillator to provide the system clock as well. Like, we don't have to connect an additional oscillator with the system clock. If we see here the clock oscillator configurations in this block diagram, here primary oscillator is this one. This is the system clock source. We can do is we have an option not to connect any crystal oscillator with this primary oscillator, and we can just connect a secondary oscillator with timer 1 and use it for timer 1 also and as a system clock also. But it is not usually recommended because this is a very low frequency oscillator and this is a low power oscillator, and usually it is not an efficient way to run our processor on. So I would suggest that we use the primary oscillator independently and we use the secondary oscillator dedicatedly for timer 1 only. Okay, then we have these prescaler bits as I told earlier. Then we have the timer 1 oscillator enable bit. So we can enable or disable this timer oscillator right here. This is the timer 1 oscillator enable bit. So we can disable this oscillator when we are not using an external crystal oscillator and we are using the external clock as a using it in a counter mode, or we are using the internal clock as the clock source for the timer. So to save power, we can disable this resonator because it is not being used. Then we have the timer 1 synchronization bit. So if we are using an external clock source for the timer, we have an option to synchronize it with the internal clock. If we are using an external clock, we want to use it independently. We don't want to synchronize it with the internal clock. Then the last two bits are the timer 1 clock source selection bit. We are using the internal clock or the external clock, and the timer 1 on off bit. So to start or stop the timer, we use this bit just like in timer 0. So this is your timer 1. We have seen that there are a couple of more options as compared to timer 0 available in timer 1. So let's write a program for timer 1 also, and what we are going to do in this program is we are going to try and make a real-time clock using timer 1. So in this case, we will be exploring the external clock option of the timer, and also we will be using the interrupts of timer to increment the seconds count. So in a clock we have seconds, minutes and hours count. We already have that code with us. We made a digital clock in assembly language also, and we made a digital clock in C language also. But in C language we only made a clock for the seconds portion. But in this code today, what we are going to do is we are going to make a complete clock with hours, minutes and seconds, all of them. We will take help from our previous code that we developed for the seconds count using manual delay. So let me open that code first. I will copy that code of the seconds portion of clock here. So this is the code that we developed for the seconds part of the real-time clock. But in this code we were generating the 1 second delay using this for loop. What we are going to do today is we are going to eliminate this delay subroutine, and we are going to use interrupts instead of that. Also we are going to use timers in interrupt mode. So we are going to use timer 1 to generate a precisely 1 second delay for our clock. Also in this code what we had was only the seconds part. So for minutes and hours, what we can do is we can just copy and paste this section for the hours and minutes also. So I will declare all the characters for minutes and hours. Minutes higher register and minutes lower register. Then hours higher register and hours lower register. So these are our declarations. Then what we want to do else is we want to create an interrupt ISR. So let me copy that. The interrupt ISR will be placed just above the main loop here. This is our interrupt ISR. What else do we want? We had declared a function of decimal adjust. So this decimal adjust, what it did was it used to convert the hexadecimal numbers into the BCD numbers to easily display them on the 7-segment displays. But this was doing the decimal adjust for only the seconds. What we can do here is we can define separate decimal adjust functions for hours, minutes and seconds. So DA decimal adjust SCCS for the seconds. Then we can define two more functions, the decimal adjust for minutes and the decimal adjust for hours. So this was our decimal adjust subroutine for the seconds. Let me change the name, DA SECS. I will just copy and paste this subroutine 2 times more for hours and minutes. So now this is our DA minutes and then this is our DA hours, and inside that also I have to change all these variables to hours and minutes. So let me change them also. So here I have changed the subroutines are exactly the same, if you can see here, but I have just changed the variables. Okay, what next do we want to do is we want to initialize all our registers, and we want to do the setting of timers, ports, interrupts, etc. So that we have to do in the main function. First off, we want to declare the ports as the output ports. So in our previous code, as we were only using the seconds, so we only declared the port B as an output. What we will do now is we will declare the port C and port D and port A also as the output ports. So here we go, port D and port A are also the output ports along with port B. Then we want to initialize our timers, interrupts, etc. So as we are using the timer 1, we want to set the T1 con register. And what should be the value of T1 con? And let's open the data sheet and see. We want to enable the 16-bit read-write mode. So we want to set this bit as 1. Then we want to we are not checking this flag, so it will remain 0. We are not using any kind of prescaler, so these 2 bits will be 0. Then we are enabling or disabling the timer 1 oscillator. So yes, we are enabling the timer 1 oscillator because we are going to make a real-time clock and we are going to connect a crystal oscillator with the external oscillator pins of timer 1. Let me tell you beforehand that the simulation is not working in Proteus, so we'll not be able to realize that. But for now, let's enable this pin. Then we don't want our external clock to synchronize with the internal clock. So we are not synchronizing the external and internal clocks. So we will set it to 1. Then the clock source, we are going to use it, the external clock. So we will set it to 1 as we can see here. And then finally the timer start stop bit, we will keep it as 0 for now, and we will turn the timer on after all the settings are complete. So we want to move 1 0 0 0 1 1 1 0 in the timer 1 control register. So let's do it. 0 B 1 0 0 0 1 1 1 0 in timer 1 control register. What else we want to do? We want to enable the global interrupt. GIE is equal to 1, peripheral interrupt PEIE is equal to 1, and we want to enable the timer TMR1 IE. The timer 1 interrupt enable should also be set to 1. So now the timer configuration is complete. What else do we want to do? I think now we should move on to the incrementing of seconds, minutes and hours. But now we want to do all that inside the interrupt subroutine. So we can wait at while 1 unless there is an interrupt. So while 1 will after configuration we will keep waiting, and let me turn on the timer 1 at this stage. TMR1 on is equal to 1. Now all what's left to do is to write the code inside this ISR. What do we want to do inside this ISR? When will the interrupt come? When the timer will overflow. And when will the timer overflow? After completing 1 second. So after completing 1 second, we want to increment the seconds. And then we want to decimal adjust the second and check whether after decimal adjusting it, it is greater than 60, greater than or equal to 60 or not. And accordingly, we want to increment the minutes, decimal adjust them and check whether they are greater than or equal to 60 or not. And then accordingly, we want to increment the hours and decimal adjust them and check whether the hours are greater than or equal to 24 or not. So all that we are going to do inside our interrupt service routine. So let's start writing our code inside the interrupt service routine. So the first line, the first thing we want to do is seconds plus plus. We want to increment the seconds count. Then we want to decimal adjust the seconds. After decimal adjusting, check if seconds is greater than or equal to 60. Is it right? Just 60? Because after decimal adjusting, this number is BCD or decimal. This number is BCD. And how to represent BCD numbers? In hexadecimal format. So we have to write 0 cross 60, not just 60. That will result in unusual counts. So you have to be very careful when representing BCD numbers. Always represent BCD numbers in hexadecimal format. So now, what if the seconds were greater than or equal to 60? What we want to do? We want to increment the minutes and set the seconds to 0. Minutes plus plus. After incrementing the minutes, again decimal adjust the minutes and then check what? Whether the minutes are greater than or equal to 60. Then what if the minutes are greater than or equal to 60? What we want to do? We want to clear the minutes is equal to 0 and we want to increment the hours. So hours plus plus. After incrementing the hours, what we want to do? DAHRS, decimal adjust them and see now if the hours are greater than or equal to 24. Again 0 cross 60 in minutes also and 0 cross 24 in hours also. And if the hours are greater than or equal to 24, I simply want to clear the hours. So at the end of this loop, what we want to do is we want to update the values of hours, minutes and seconds onto the actual ports to display them to the user on the 7-segment display. So what we can write is port A is equal to hours, the updated value. Port B is equal to minutes. Port D is equal to port D is equal to minutes and port B is equal to seconds in our case. And the final thing that we want to do before exiting this interrupt service routine, this ISR, is to clear the flag of timer 1 that caused the interrupt. So we will clear TMR 1 IF is equal to 0, so that after the timer is full the next time after 1 second, this interrupt will occur again and then we will run this loop once again. So I think this code for the clock is complete now. Let's try to build it. The build is successful, and now what we want to do is we want to simulate this code on the in the Proteus. So if we see here, let me tell you beforehand that I tried to connect this crystal oscillator with the T0, T1 OSO and T1 OS 1, T1 OS 0 and T1 OS 1 to use the external clock source, to use the crystal as an external clock source for timer 1, to use it as an RTC, and this crystal frequency I set it to let's say 65536 Hertz. The issue is that Proteus is not simulating it correctly. It is not taking this, it is not activating the crystal oscillator. So I had to use an external clock source, not the oscillator source for this purpose in this case. So this is my external clock source, and if you can see here that I have set the frequency of this clock source as 65.536 kilohertz or 65536 hertz. So it will serve the same purpose. This virtual source will provide a frequency of 65536 hertz to the timer 1 oscillator, and the timer will count up based on this frequency on every pulse on this external pin, because we are using the external oscillator. If we see here in the code, we have if we go to the configuration, we are using the external clock source for timer 1. This is the T1 con register, and here T1 OSEN, the timer oscillator enable bit will be cleared and it will not be synchronized, and the external clock will be selected. So that would be 0 1 1 0. Here we will set it to 0 1 1 0. So let's see whether this was already uploaded with the lecture 31 production.hex. Okay, so let's run this code and see whether it is working fine or not. So currently our display shows nothing. There are all zeros and there is no increment. So let's try to find out what's wrong with our code, why these values are not being incremented. Alright, so it seems like there was nothing wrong with the code, but there was one wire that was coming from this oscilloscope that was wrongly connected with this with the one of these pins. So once I removed that wire, I tried to simulate that code again, and now it is working fine. So there is nothing wrong with the code. I have not changed anything in the code because I couldn't find anything, and then I proceeded to see if there is something wrong with the simulation circuit itself. So I had accidentally put some wire here that was fiddling with the oscillator circuit. So now you can see that the seconds are incremented after 1 second each, and the display is now correctly showing the seconds. The minutes and hours are still 0. So we'll wait until the seconds become 59 and then overflow to 00 and the minute is incremented, and then we'll stop our simulation here and we'll assume that the rest of the simulation is working fine. So let's wait. Okay, so here you can see that the seconds have been reset to 0 after reaching 59 and the minutes have been incremented. So we can safely assume that our simulation is working perfectly fine according to our logic. One thing I want to emphasize here is that at this point in the code we have enabled the timer, or we have started the timer, turned it on, and nowhere in the code we are turning it off again. That is because we don't want to get any error in this approach. What will happen is that after the timer is turned on, it will keep running in the background, and in the background the timer will keep incrementing, and once it will reach the maximum count of 65535, it will overflow and it will be reset to 00, and at that point the timer flag will be set. The TMR1IF, the interrupt flag, will be set, and at that very moment the timer will force the processor to stop its current task and jump to the interrupt service routine at that very moment when the interrupt comes. So when the processor stops its current task and jump to the ISR, inside the ISR we have many different conditions that we have to check. So if we start checking these conditions and we stop the timer in the background, there are maybe 10, 20, 30, even 50 microseconds being consumed in this loop, in this highlighted portion. So if we stop the timer, all these instructions, all this portion will become the error that will be keep accumulating in our final time period. So what we do to avoid this is, once we enter the interrupt service routine, we keep the timer running, we leave it alone, we do not stop it, we leave it running. So we start checking these conditions. Now while checking these conditions, the timer is still running in the background. So let's assume for instance, after all these conditions have been checked and whatever was required has been done, the timer has reached maybe a count of 100. Now I update the values of the hours, minutes and seconds on the respective ports, and then I just clear the timer interrupt flag. So the timer keeps running. Clearing the interrupt flag will not affect the current state or current value of the timer. So once this flag is cleared, I exit the loop. I exit the interrupt service routine and I go back to where I left when I jumped to the ISR routine, and that was while 1. I was just waiting. I was not doing anything else. So the processor will return to this line, line 136 while 1. Now at this point the timer has already reached maybe a count of 110, and it will continue counting up from that value, from 110, 11, 12, and once it reaches again the maximum value of 65536, again the overflow flag will be set, and again an interrupt will come and it will jump to the ISR, this routine. So we have not lost any time in between by leaving the timer running in the background. So that is one very big advantage of the peripherals. Peripherals are all the blocks inside the microcontroller that are independent of the processor. They run in the background in parallel with the processor. The processor is not being involved when we are running or we are doing anything with a peripheral, and timer is one of those peripherals. If we are generating this delay manually, then the processor is involved in generating that delay, and we cannot avoid the error. We can minimize it, but we cannot completely eliminate the error. So using timer in conjunction with the timer or peripheral interrupt, we can completely eliminate the error and we can get a real-time clock without any error. So this example, I hope, will clarify the use of different modes of timer, different available clock sources of timers, and using interrupts for timers. How to use interrupts for timers. In this particular example, we were not doing anything else. We were just waiting. But this while one is not always while one stop here and wait here. We can do some other task in parallel while waiting for the timer to overflow. And in the next example, we are going to do that. What we will do in our next example, we will use two timers at once. We will use one timer just like this timer 1, to generate a delay of 1 second and use it for the RTC, for the clock, and we will use another timer in parallel, and that timer will be used to generate a continuous waveform on one pin of the microcontroller. And how we are going to achieve that? We are going to use the interrupt for both of these timers. So both of these timers will be used in interrupt enabled mode, and we will do that example in the next lecture. For this lecture, this is it. I will soon upload the next lecture also, and in that lecture we will discuss the remaining two timers, that are timer 2 and timer 3. We have already discussed timer 0 and timer 1. So most of the things related to timers have been covered. We will quickly cover the remaining two timers, timer 2 and 3, and we will mainly focus on the differences of those timers with the already discussed timer 0 and timer 1. And then we will do an example based on that, and then in the same lecture we will switch to the CCP, ECCP peripheral of the PIC microcontroller, that is capture compare module, and that is very useful for generating pulse width modulation, PWMs. So that's it for today's lecture. If you have any questions, please post it in the respective week 12, and I'll be more than happy to answer. Till then, stay safe, take care, Allah Hafiz.